Hi, after a quick module on decision trees, we're going to spend two modules discussing linear methods for classification. Recall that we started the machine learning segment of the material by talking about two different classifiers. One is a nearest neighbors, and the other is a linear approach. Here in the linear approach, which we're going to explore in more detail, we have data x, which will often be multidimensional, it's a vector, and it takes values in a class G. G has k possible labels, 1 through k, and we want to predict G of x. So as usual, we're going to have training data, we're going to have test data, but we want to predict G of x well. So we're going to create affine functions, fk of x, for every class lowercase k, where k is 1 through capital K. And for each of those lowercase k's, fk of x will be beta 0, an offset, plus beta transpose times the data x. So beta transpose is a vector, a row vector, and x is a column vector. Row times column is equal to scalar. Scalar plus the scalar b0 is equal to scalar. We'd like that scalar after training to be close to g of x. So first of all, two comments. First of all, this is an affine function, not a linear function. A linear function is required to go through the origin, meaning a linear function of 0 is 0, but depending on the value of beta 0, this is likely not a linear function. Secondly, beta actually depends on k. So beta 0 is a function of k, and beta transpose is, again, dependent on k. So what we're going to do, we're going to run these linear scores, and one way to think about it is that these linear scores, the higher they are, the more likely you are to be in class number k. And we're going to choose g hat, the estimated hat as a function of x, is among the capital K functions, among the capital K scores, we're going to choose the class lowercase k that gives you the highest score. That's why we have argmax of fk of x, argmax over the k's. Now, what if fk of x is equal to fl of x for k and l both being elements of the set of possible classes from 1 to capital L? In this case, we have a decision boundary between two classes. The two scores are equal, and choosing either would be appropriate. So let's try to see this through an illustration. We have data from three classes. The three classes are illustrated by colored numbers with blue, orange, and green. And this was just chosen from the book. If some of you have problems with these colors, that's just how it is. Let's look at two varieties of linear classifiers. One of them, the panel to the left, has linear boundaries, whereas the panel to the right has quadratic boundaries. So what do we mean by linear boundaries? We had linear functions, and this is called linear discriminant analysis, or LDA. We're going to talk about LDA details in the next module. And because these are linear functions, it turns out that the decision levels, the locations where they're equal to 1, there happen to be straight lines. Now, with quadratic functions, we add cross terms, products of two variables, x1 times x2, and also squares of individual variables. We add them to the space. We run LDA over this quadratic, this space that contains quadratic second-order terms, and we get more complicated boundaries, quadratic types of boundaries. Now, just illustrating again, this is for purposes of getting intuition. One thing that you're seeing is that the linear classifier, its results are somewhat crude because it separates classes in straight lines. This area, we're making an error. This area contains the oranges too, and this area also contains oranges. So in these three areas, we seem to have oranges, but they're not classed as orange using our linear boundaries. On the other hand, with a quadratic approach, yes, we miss this one over here, and there are a few ones that we miss over here, but overall, with quadratic types of boundaries, we get better performance. So QDA, quadratic discriminant analysis, will be shown to be better than LDA, but there are always going to be trade-offs. So imagine that you have an indicator matrix. We're going to define k different variables. Yk of x will be 1 if the label of g of x is k, else 0. So for every x, among the capital K functions yk of x, only one of them will be 1, all the others will be 0. And therefore, we're now going to be able to train on these types of functions. We'll form the k variables into a vector, y1 through yk. All of these are a function of x. And this gives us n training instances. So we're going to have an n by k indicator matrix. N rows, a row for each of the training instances, k columns, a column for each one of these classes. We're then going to train a linear regression on this indicator matrix. Y is going to be this n by k matrix that I just described. X is the explanatory variables, and y hat is going to be the pseudo-inverse multiplied by y. Okay, so one more comment. The first column of x will contain ones. This will be possible DC offsets. And overall, what this approach does, this approach is trying to create linear scores that are close to these yk of x's in the training data, and hopefully the linear function will, for many of the x's, give the correct maximum. Recall that we're choosing the class lowercase k for which the linear functions that we train, or rather the linear or affine functions that we train, we're choosing the largest one for each of the x's. All right, so this approach attempts to find y hat from the training data that does that well. Now, is this useful? So to classify, we're going to run our k different functions, fk of x. We're going to take the argmax, and that's going to be g hat of x. And in fk of x, we're using linear regression. It can be interpreted as follows. Fk of x could be interpreted as resembling the probability that g of x has the label k conditioned on x. And there's an interesting insight here that the expected value of an indicator is probability. Now, why is that? So an indicator, let's write it IND of x is going to be 1 if a condition holds. And here, the condition could be, for example, that g of x is equal to some k. That's a possible condition. And it's going to be 0 if the condition doesn't hold. And now we're asking, what is the expected value of this? This is an indicator function. So what's the expected value of the indicator function? So we have two different values for x, either 1 or 0. So we have the probability that IND of x is equal to 0 multiplied by 0 plus the probability that IND of x is equal to 1 multiplied by 1. but 0 times something is 0, and 1 times something is itself, we're left with the probability that the indicator function is equal to 1. So we are trying to create fk of x's that are indicator functions, and this has the form that if they're good indicator functions, they're predicting the probability that g of x equals to k in a reasonable way. Of course, for typical real-world problems, it'll be unrealistic to create excellent probabilities, but maybe we can do through this type of training, maybe we can do something which is reasonable. So overall, another comment is that as the dimensionality increases, we may want to add a lot of basis expansions, for example, polynomial term, and basically run regression on all of these. Finally, I'd like to discuss that there's a limitation. A class could be masked by other classes. Here we have an illustration with 3 classes. 1s, 2s, and 3s. The 1s correspond to orange, the 2s correspond to blue, the 3s correspond to greens. And we have 3 classes. Now let's try to understand what's going on here. Let's plot this axis. Let's call it the y-axis. So along the y-axis, we have 3 different functions. The orange function is highest on the left side, okay? And the green function is highest on the right side. Now, there are different versions for the blue function, which I'll write in blue. So suppose that this was the blue function. In that case, there would be a region along this y-axis. There would be a region where the largest score among these 3 functions would be a blue, and to the right, the largest would be a green, and to the left, the largest would be an orange. And that way, we would get these, perhaps the large majority of these 1, 2s, and 3s, the 3 colors labeled correctly. However, it's also possible that and I'll try to illustrate this. It's also possible that the orange function and the green function are larger than the blue function. So the blue function is never largest. And because it's never largest, in this region in the middle, where perhaps we would like the blue function to be largest, instead of getting blue, we're classifying to either orange or green. So in this case, we have 3 classes and 2 were recognized. And in general, if we have k classes, this type of problem can be corrected using an order k-1 polynomial, but this is just an illustration that this is something that needs to be considered carefully. So the illustration is trying to show that linear classification can become complicated. So that'll be it for this module. We started talking about linear classifiers, and next time we're going to talk about the details of linear and quadratic discriminant analysis, LDA and QDA.